Assalamu alaikum, Bismillahirrahmanirrahim. Welcome to our JNCIS service provider course. So we are discussing switching section and service provider certification. Last day we discussed ERP and lag link aggregation group and ERP Ethernet ring protection. Today we discuss next that is AMC lag multi-chassis link aggregation group and virtual chassis. Okay, I think that is very important topics for you can say it can be deployed in your data center. It can be deployed in your service provider backbone, or it can be deployed with your customer. That means P2C, it can be deployed. Okay. So first, we discussed what is AMC lag and what is the virtual chassis, and later portion we configure the AMC lag and virtual chassis. Okay. So let's start. This is our today's lab, and this is our today's slide. Basically, let's follow the slide. Service provider switching. MC lag multi-chassis link aggregation group or multi-chassis lag. See the topology here. Provider router 1, P1 and P2 is connected with each other, and this device is um, it's basically switch. Basically, consider this P1 and P2 is switch, or you can consider MX, because MX can work as a switch or work as a router. Okay, so consider three devices working as a switch. P1 and P2 is in provider end, and C1 is the customer end. Okay, so if you want to add lag in customer port, in previous class we saw that when aggregation lag happened, there is multiple device, like this is switch 1 and this is switch 2. Both port is connected with each other. In that case, we configure here lag link aggregation group. So sometimes it's not possible to connect a multiple link from service provider to customer end, because if we connect a multiple link from P1, so consider P1 goes down, what happened? Customer will goes down. So in that case, we can consider another location or another pop. So if one device failed, another device will participate, or another device take over the customer traffic. Okay. So in that case, or in this scenario, we need to deploy MC lag. Normal lag will not work for this scenario or for this topology. Okay, we need to configure MC lag. Okay, so this is the topology where we deploy MC lag. So how next we discuss how it will work, or what is the function of MC lag, and how to deploy this. Okay, so say multi-chassis lag, that is the AMC lag, creates a logical lag interface between two or more devices. They are creating the logical instance between P1 and P2. That means you can say P1 and P2 logically single device. Logically single device. So logically single device can communicate with the remote CE device. Okay. So it provides node level redundancy and multi-homing support. Multi-homing in that case, you can say customer is connected from two or multiple service providers POP. Okay, so in that case, you can say it's a multi-homing. Okay, and also providing the redundancy. If one link goes down, another link will be active. So if one pop is down, another pop will be active. Okay, so in that case, I can say it provides node level redundancy and multi-homing support. Okay, P1 and P2 appear as a single network device to C1. If you look from C1, you see that both link will come from same device. But in provider in the physical device is different, but they are logically same. Okay, it removes the need for spanning tree protocol. No need to deploy spanning tree protocol interpret in MC-lag. Okay, and inter-chassis control protocol, that is ICCP. Inter-chassis control protocol exchanges control information between two MC-lag network devices. So need to deploy ICCP between P1 and P2, so that if they can establish connectivity between P1 and P2 using this protocol, that will work. Okay, so our primary uh, consideration is when we deploy MC-lag, we need to introduce ICCP, Inter-Chassis Control Protocol. Need to deploy in service provider devices. Okay, number 1 point. See another topology here. This is the example topology. So consider here multiple link from P1, multiple link from P2. You can aggregate both four links. Four links which is connected with CE1 in single MC-lag. Okay, so this is the more complex topology. C1 have node level redundancy. So you can say customer have node level redundancy, also link level redundancy. Service provider also have link and node level redundancy. Okay. So next, MC-lang redundancy example. Link level redundancy, but node level redundancy on the provider side only. Customer side don't have node level redundancy, only link level redundancies exist. So if you consider node level redundancy in customer and service provider in, your topology will be this. And this network, I think more redundancy will make, and this network will give you high availability compared with this. Okay. So MC lag state. You can deploy MC lag as a active standby. Active standby. That means this link will work as an active link, and that will be the standby link. So this can be one solution, and another solution can be active. You can send traffic from CE1 in both link, and that will work as an active. That is possible. Okay. So MCLAG is that active standby supported. When you deploy active standby mode, active link standby link, active standby mode. So your device all device, all Juniper device don't support this basically active standby. If your line card is a dense port concentrator or DPC or modular port concentrator, that is MPC. If your device have DPC or MPC card, MPC line card, it will support MCLAG active standby mode. Otherwise, not. So first, if first you have to check. You have to check your device have DPC or MPC line card. If yes, then you can deploy. Okay, one node active at a time. One node active at a time. That is active standby mode. Okay. Then next, active. Active only support line card is MPC. No other card support active MCLAG state. So both nodes are active. Both you send traffic in both link. Both link will work uh, as a active link. Okay, uses an inter-chassis link, that means ICL, between providers and PE devices. Uses an inter-chassis link, that means ICL, between provider edge devices. You need to introduce this one, inter-chassis link. If MCLAG active state, if you want to deploy this one. So next, MCLAG state traffic flows. How to flow the traffic. When consider active standby, so consider this traffic destined to R1. This is your router 1. Traffic destined to router 2. This is router 2. So this is the C router. Your traffic will first come in P1. If destination is R1, follow the blue link, and if a destination is R2, follow the green link or green line. Okay, so next, when you configure or deploy active mode, active in active mode, need to they are just consider here traffic destined to R1, traffic destined to R1, and this green line traffic destined to R2. Consider this blue line P1 to router 1, P1 to router 1, and traffic destined to R1. This blue line is first come in P2, then go to P1, then R1. That means every packet, every packet is load balancing between P1 and P2. That is called the active. So both P1 and P2 are active in that case. So MCLAG configuration CE1 device. Basically, CE1 device configure the MCLAG. Just configure the aggregate interface first. If you deploy or configure aggregate interface in Juniper devices. So the process is set chassis aggregate devices, Ethernet device count, then you can set the number. Here, the setting number is 1. That means only one aggregate interface is created. That is AE0. And under AE0, both interface, the physical interface will be the member. The physical interface, both interface will be the member of AE0. Okay, so first need to create the aggregate interface, then add those interface under the aggregate interface or lag. Okay, this is the same configuration statement like lag, single normal lag. But in service provider, in there is there will be the multiple configuration. So first we introduce interface, create aggregate interface fast. So create set, first configure C set chassis aggregate devices Ethernet, and the device count you can set multiple. This number basically depends on device model. This device support maximum 496 aggregate interfaces. So for our lab testing, I set here one. So how to check this one? Run show interface stars and mass AE aggregate interface. See here, our aggregate interface is AE0 and the interface status is down. Okay. So next is slide 13, MCLAC configuration P device child links. Set P device child links to 800 to 380, configure 800 to 380 to use the A0 interface. So in P1 and P2, they are attaching the physical interface to aggregate interface. So need to configure same thing in P1 and P2 also. P1 and P2 also. And the status, check the status, and that will be down. Okay, that is down. So fine. The next, add the physical interface to aggregate interface. Okay, so check this one. P1, go to our topology. P1 interface is 1 and the P2 the interface is 2. So P1 set interface GE 0 by 0 by 1 gig ether options 800 to 80 and our aggregate interface is A0. That is okay for P1. Commit this one. And for P2, our interface is for P2, our interface is Z0 by 0 by 2. So same thing, just changing the interface number. Commit this one. So memory interface added. Memory interface added. Then configure ICCP. Configure Inter-SASIS Control Protocol. ICCP configuration. ICCP configuration will be happen between P1 and P2. So ICCP configuration currently supported between two P devices only. Peer concept, interface or loopback peering recommended. You can use interface or loopback, but loopback is recommended. So if a P1 can get get raised to PE2 loopback, so need to introduce one ICP protocol between PE1 and PE2. Otherwise, loopback interface IP can't raise another router loopback interface IP. Okay, so in that case, need to introduce OSPF or any other ICP. So consider here our example IP address is 10.10.1 and 10.10.2. P1 is 10.10.1 loopback and another P2 is loopback is 10.10.2. So set same in our topology. So set here hello 0 dash 10.10.10.1 slash 32. So this is P1 and another router loopback is 10.10.2. Another router loopback is 10.10.2. Okay, that's fine. And make one ICP between P1 and P2. That is simple. Set set routing options. ID. Router ID is 10.10.10.1 and set loopback interface. Set interface LO0 unit 0 sorry, hello 0, unit 0, description, L double O, P loop back, and the IP is 10.10.10.1/32. Make mistake here, family inet address. My address is 32. Okay. Loopback interface configuration done. Then set interface ZE 0 by 0 by 0 and the unit 0 description is P2 router. P2 router. And family inet address is 192.168.12.1/30. Commit this one. So this is basic interface configuration. We'll display set. Some configuration already added. Okay, no issue. I'm configuring loopback. So copy this loopback interface, and the loopback interface here. Loopback interface is 2. Okay. Then setting the router ID. Router ID is 2. Okay. Router ID is 2 configuration. So then configure interface ZE, that is P1, and the IP address will be 2. Okay. So commit this one, matching the configuration from both router or ZE interface configuration done. Loopback interface configuration done. Setting router ID configuration done. Okay. Then ICCP configuration. There is the sample configuration of ICCP. So before going to ICCP, need to introduce one IGP. Set protocols, OSPF, area 0, interface, LO0, passive. And another interface is Z0 by 0 by 0, and the interface type is P2P. So this is our OSPF configuration. Checking again our OSPF configuration that is identical for P2. Copy this one. Okay, that's fine. Done. Check the OSPF status. Run show OSPF neighbor. OSPF neighbor is up. OSPF neighbor is up. Checking the loopback from router 1 to router 2. Run ping 10.10.2 and the source will be 1. It's working fine. And then ICCP. Configure the ICCP. So edit protocol ICCP. Then under ICCP, set here the local address. Local address is self loopback address. Peer address will be our peer loopback address. And redundancy group ID list, you can set here any number. I set here 1 because this is the first one. Liveness detection, it is basically BFD. It's basically BFD configuration. Okay. So these all are ICCP protocol configuration, just setting the peer address. So logging this one, ICCP local IP address is this, peer address, redundancy group ID list, and BFD configuration. A similar configuration is required on PE to accept use of the local and peering IP address. Just same thing will be happened in PE2. ICCP uses the redundancy group ID to associate multiple chassis that perform similar redundancy functions. So need to configure same thing in PE2. So check this one, commit this one first, and then check this one in P2. See the P2 local address, PR address, and other setting is identical. My PR is 10.10.1. From P1, the PR is 10.10.2. Okay, that's good. So ICCP configuration done. Done. After ICCP configuration, need to check BFT session. Need to check BFT session. Session is working or not. Okay, so run show BFT session. See here, the BFT session is up. Okay, check from both device. The BFT session up. Okay, that's good. Our BFT session is up. You can take detail from here. Okay, then go next. Configure active standby mode. We're checking active standby mode. So for active standby mode, the P device have the same configuration but with two difference. Active standby mode, the P devices have the same configuration but with two key differences, SASIS ID and status control setting. So see here, this is the P1 sample configuration and this is the P2 sample configuration. So P sample configuration, that is under A0 interface, that is aggregate interface. Aggregate ether options, and that is LSCP, active, periodic fast, then set the system ID, admin key 1, system ID 01, system ID 0001, identical. Everything is identical. MC aggregate, MC ID1, redundancy group 1, redundancy group 1, chassis ID. P1, the chassis ID is 0 and this is the chassis ID is 1. Status control active and status control is standby. And the will be aggregate interface will be bridge layer 2. Family bridge interface for trunk VLAN ID list. You can add any VLAN ID. Okay. So need to create a VLAN ID. VLAN ID example VLAN ID is 500. So let's create one VLAN ID in P1 and P2. Set bridge domain. Set bridge domain VLAN ID 500. VLAN ID is 500. So our VLAN ID create done. VLAN ID is 500. So same thing will be in P2. So VLAN ID create done. Our aggregate interface is A0. Aggregate interface is A0. So create the sample configuration for first P1. So clear the screen. Okay. Edit interface A. So we are creating aggregate interface A0, right? So interface starts mass AE0. Yes, A0 interface is exist. Edit interface A0. I'm under the A0 interface and set aggregate ether options LSCP and LSCP mode is active. LSCP mode is active. So then LSCP mode is active. Then you can set multiple parameter of LSCP. That is one is periodic. You can set periodic fast. They send packet between two devices every second. That is called fast. Okay, then LSCP other options. ID. System ID. The example system ID is 00:00:00:1 2 3 4 5 6. Exact MAC address 1 2 3 4 5 6. Okay, 01. System ID is 01. Then admin key just for identification. Admin key and system ID is used for identification. Admin key, I said here 1. Okay, check warning. MCAE must be configured for admin key. MCAE, multi-chassis aggregate interface. I'm not creating it MCAE, that's why I'm getting the error. Okay, so next, set aggregate ether options, then MCAE. See here, MCAE, multi-chassis aggregation network device configuration. MCAE, then next, MCAE ID. The ID range is 1 to 65,535. MCID, I said here MCID 1. Then redundancy group, MCID, then redundancy group. You can take help. This is the redundancy group. I said here the redundancy group is 1, and chassis ID. Chassis ID. Chassis ID I said here 0, and the neighbor device chassis ID will be 1. Setting done. Then status control. Status control. Status control is active. This device work as a active device. So I configure here status control active, and another device we configure here standby. Okay, so that is active, and see the configuration, everything is okay or not. This error goes. And last, final warning, missing mandatory statement mode, the interface mode. Okay, so need to set the interface mode. Set unit 0 family. Family will be breeze. Family will be breeze, and the interface mode will be trunk. Okay, and the villain ID list. Villain ID list is 500. We already created the villain ID 500. Okay. Now checking the configuration. Uh, Still now getting commit check. Missing mandatory statement mode. Mandatory statement mode. MCAE mode. Chassis ID status control active. Status control active. Chassis ID redundancy group. So set aggregate ether options. MCAE switchover mode. This is mode. Mode is active standby. We are configuring active standby, not active. So that is final active standby. So this configuration is missing here. I don't know why missing. So this is our exact configuration. Let's set. This is the exact configuration of uh, active standby mode. Okay. So we can copy this one. Our aggregate interface is same. We can copy this one, just change the chassis ID will be 1 and the status control standby. So we can set here relative. Our command is reduced. Then edit interface A0, A0. So copy this one. This basically same or identical chassis up to chassis. So copy this one, done. Chassis ID will be 1, 1. Then that is mode will be active standby. That is perfect. And this status control will be standby. Status control will be standby. And the port is status, interface mode trunk, and allowed VLAN will be 500. So that's all. I think SSID 1 and status control standby. So I'm making changes. Active standby configuration, commit check. The configuration is okay. Then final commit in P1. It's okay. Then I'm now 17. Now checking LSCP interfaces. Show LSCP interfaces. Basically two comments here. Show interface MCAE and show LSCP interfaces. So checking this one in P1 and P2. P1 and P2. Run show LSCP interfaces defaulted detached. So checking here the status current and mux stat collecting distributing attached. So we're not configure lag in CE1. That's why we're getting defaulted or detached. Okay, so that is the reason. So checking also getting same thing. So show display set. Checking in customer router AE interface is created, but I think not addressing the member interfaces here. Only adding the interfaces, nothing will happen here. So need to add. So copy from here, show display set. The interface is 1 and 2. 1 and 2. So I'm copying this one. 0. Interface 1 is coming, and here interface 2 will be the member of A0. Both interface will be the member of A0, and the aggregate interface will be the layer 2 interface. Aggregate interface will be the layer 2 interface. That means um, if I want to send same VLAN from customer end, so need to configure the VLAN ID and need to configure also A interface, A0 interface. Okay, interface mode trunk, and this is the VLAN ID, allowed VLAN ID. So let's check, commit check. Our configuration is okay now. So checking the configuration in customer router, aggregate, this is the aggregate lag interface, and these two are the member interface of lag, and this is the VLAN. Okay, just checking the LSCP interfaces status again. They are not communicating. That is defaulted or deducts. but marks state detached. Checking from here, getting same, defaulted, interface not getting up. Run show interface AE0, run show interface AE0. All device don't support MC lag basically. Okay, so see here AE0, and that is MCAE1 is standby enable, physical link is down. Physical link is down. We're getting the link is down. So again check this link is down. So I think need to check ICCP first. If ICCP will work, then this will work. Okay, so uh, another command is show interface MCAE. Run show interface MCAE. So the local state is down, local state is active, peer state is standby. So if I say run show ICCP, ICCP established. ICCP is established. Liveness detection is TCP connection established, redundancy group is established, uh, the ICCP client, okay, it's working. ICCP working, but not getting this link up. Okay, checking further. So if we configure active mode, if we configure the active mode, the configuration changes only this one. Multi-chassis protection, the PRIP, and set the interface. Same thing will be happened in PE2, and here configuration will be changed. Both mode is active. Both mode is active. And status control, this is active and this is standby. This is the difference between active and active standby configuration. So this is the active mode configuration. Show interface MCAE. Need to check our MCAE is basically down. MCAE is not working as expected. Okay, and MCA active state active and local state is down. Peer state check, local state down. Okay. Because this configuration basically have some line cut dependency. We are using a virtual, that is PMX, that is not DPC or MPC line card. That's why we're not getting the protocol up or not getting the LSAP interface is current or connected. Okay, but the configuration is same. The configuration is same. Okay, so this is the sample configuration of multi-lag. So when you configure MPC MX devices, so which have MPC card or DPC card, so a DPC line card, it will work. Okay, so run show chassis, how to check this one? Run show chassis, run show chassis hardware. Here you will get the MPC status here. This card is basically not the MPC or DPC supported. It's a virtual. That's why we are not getting the protocol app or lag or MCA or LSAP interface not getting up. So okay, we're just showing you the sample configuration of multi-lag. That is mode is active is standby. The step is very simple. The step is I just Recall the steps. First, need to need to configure AE interface. You can set the number, depends on your requirement. Next step is adding the physical interface under the aggregate interface. Then under aggregate interface, you have to configure LSCP and MCAE configuration. Okay. Last one is you have to configure ICCP so that one switch can communicate with other switch through ICCP protocol. Okay, that's all. Now we are going to question and answer section. Which part of the ICCP configuration is used to associate the multiple chassis performing similar redundancy functions? Redundancy group list. Which command is used to verify that the MCLAG works properly in the active standby mode configuration? Show ICCP. Which command is used to verify that MCLAG works properly in the active standby mode configuration? That is basically it's a multiple copy, I think. Multiple copy. First copy will be wrong. Uh, Taking here multiple copy. Sorry, this will be wrong. I'm just remove this one, removing this one. Okay, okay, then start. Basically, show interface MCA. This result will show you it works or not. I'm also checking this verification. I'm getting down. That means because this device not supported or this not the DPC or MPC line card. This is the reason. Okay, so match the benefits of same select modes under this category. Uh, we are discuss MCLAG will be two type is active standby mode and another will be active mode. So in active standby mode, only one P node is active at a time. That is true, and it is supported on both DPC and MPC line cards. But in active mode, it is supported on MPC line cards only. Okay, all links between C and P devices are active. This is the difference between active standby and active mode. And next topic is MX virtual chassis. Virtual chassis. That is consider here two physical router 240 and that is another 240. So they are just communicating with BCP port, virtual chassis port. Okay, so see here, MX series virtual chassis provide inter-chassis redundancy as opposed to intra-chassis redundancy. Consist that means you can set redundancy between two MX devices through BCP. That means virtual chassis. Consist of two identical MX series. The requirement is both devices will be identical. That means MX240, MX240, MS2K, MS2K, MX960, MX960, like this. Consider two identical MX series devices connected through dedicated virtual chassis port, that means BCP ports, on modular port concentrator or modular interface card, that is MPC or MIC interfaces. Okay, combined into one logical device for simplified management. That means both consider these devices are separate and these are the physical devices. You want to combine both physical devices in single one. So this technology is called the virtual chassis. And you just log in, you are just getting one management IP, you just logging one device, you will get both devices in single CLI. So that is the virtual chassis consideration. Inter-chassis redundancy prevents network outages and protects routers against access link failures, uplink failures, and wholesale chassis failures. That means here considering if one routing engine is failed, another will work. Device level redundancy. If one line card is problem in one physical router, another line card is okay in another router. So you have link and node both redundancy here. A robust inter-chassis redundancy implementation enables service provider to fulfill strict service level agreement. So in that case, you will meet the strict service level agreement, basically in node level. Avoid unplanned network outages to meet the needs of these customers better. So this is basically overview. Virtual chassis model approach provides inter-chassis redundancy, enables a collection of member routers to function as a single virtual router. This is the main theme. The interconnected member routers in a virtual chassis are managed as a single network element. Okay. So managed by virtual chassis, con- that is a VCCP, that is virtual chassis control protocol, dedicated control protocol based on ISS. That is the dependency. That is the dependency. Need to introduce ISIS. Supported on MX240, MX480, and MX960 devices with MPC and MIC interfaces. That is the dependency. You don't deploy any devices. Should be MX, this model, and this interface card, that is MPC card. Otherwise, not. Graceful routing engine switch server, that is Grace, non-stop active routing NSR must be enabled on both members of the virtual chassis. This protocol will be enabled on the. This is basically in software part. Okay, but in physical consideration, MX240, MX480, MX960, and with MPC card if you want to deploy virtual chassis. Any device you can't make virtual chassis. Okay. Virtual chassis benefits. These are the simple benefits like simplifies network management of two routers into one logical system, provides resiliency against network outages and protects member routers against access link failures, uplink failures, and chassis failures. Same thing. And extend the high availability capability of applications such as Grace, NSR, bind a single MX series device to both member routers in the virtual chassis. So you will get great availability feature or redundancy feature under virtual chassis. Enable service provider to fulfill strict service level. Well, same thing. Virtual chassis components, multiple VCP are possible. You can add multiple. You can consider one router is primary router, another router is backup router. Virtual chassis primary router, that is protocol primary. Virtual chassis backup router, that is protocol backup. No dedicated line card roles in a two-member MX series virtual chassis. Virtual chassis ports. It is recommended to configure virtual chassis ports only on 10 gig interfaces. Virtual chassis ports will be configured in 10 gig interfaces. Okay, this is another consideration. And the primary and backup router duties when both router will participate in virtual chassis event. So in primary router, they are doing manage both primary and backup routers, runs chassis management process, control protocols, receives and process all incoming and exception path traffic destined for the virtual chassis. Propagate the virtual chassis configuration, including member ID roles, configuration group identification, application, virtual chassis members, everything. And what is the duty of backup router? Takes the primary role of the virtual chassis if the primary router fails. Simple. Thus preserving routing information and maintaining network connectivity. Okay. Synchronizes routing and application state, including routing tables, subscriber state information with the primary routing engine. Basically, they are always communicating between them. Relays chassis control information such as line card presence and alarms to the primary router. Okay. So this is the duty of primary and backup router. Okay. So next question and answer section. And there is no configuration basically. Mm, which ASA feature is used to protect the routers against access links and wholesale chassis failures? That is inter-chassis redundancy. Intra-chassis, not the intra-chassis. You know, in MX 480, MX 240, 960, both have multiple routing engine. But this is intra-chassis. This is intra-chassis. This is not the inter-chassis. So, if you consider inter-chassis, that will be physical notable redundancy. Okay. So, our second question is which component acts as a special Ethernet interface between the member routers in a virtual chassis? Virtual chassis port will work. So, this is basically lab. So, I think I have finished our today's topics. That is MC lag and virtual chassis. So, is there any query or question? Hello.
Oh, no questions, sir. Okay.
Okay. Prakash, how are you?
You're fine, sir. You're good, sir.
Okay. Thank you. In our today's lab, we are checking here VMX device and the version is 14. Basically, multi-lag chassis need MPC line card or DPC line card to check multi multi chassis like is working or not. But it is the virtual device that have no line cards here. So in that case, I'm just showing the sample configuration and the steps. If you have physical devices, you can configure those one and follow the steps. Hope it will work. So thanks. Thank you very much. Bye bye.
Thank you, sir. Thank you. Bye-bye, sir.